certain matrix A reduces down to this matrix, then what's the basis of the row space? Can we find a basis of the column space? Can we find a basis of the null space? Okay, well, what can we determine? Well, from the row space, to get the basis of the row space, as we've seen, the non-zero rows form a basis. Okay, so our row space could be spanned by this. So the basis of our row space. We can't determine the basis of our column space unless we know the original matrix A, because that information, the specific information about the column space has been lost in reducing the matrix. Now we still retain some information, namely that the columns with leading ones would indicate which columns in the original matrix contain the basis for your column space. Now, this matrix is not completely reduced, but of course we could always divide this row by 1, divide this row by 2, and it would be, and we would have leading ones here and here. So we can determine that column space would consist of the two columns in the A matrix corresponding to, well, the first and second column of the A matrix. Okay, so I think I'm going to ask you to do that. Okay, I don't think I did ask you to do that. Never mind. Okay, what I actually ask you to do on the homework then is to do a couple of row operations and build this reduced matrix back to some matrix that doesn't have an obvious reduced form, and then use that matrix as a basis for constructing your column space. Okay, well, the null space, in any case, as we know, and of course we've been over this, consists of all the vectors such that the matrix multiplied by that vector gives us the zero vector. And that's equivalent then to saying for this matrix, if this times the x1, x2, x3 vector is equal to the zero vector, then 3 times your x1 plus 1 times your x3 has to equal 0. Well, there it is. And 2 times your x2 plus 1 times your x3 is going to have to equal 0. Well, there's that equation. So we translate that back into two equations, and then we say, okay, well, we have a free variable here because we have 3 variables, 2 equations. So x3 we're going to call t. Okay? And in that case, x2 is negative 1/2 t, and x1 is negative 1/3 t. Very easily determined by substituting t for x3 in both equations, solving for x1 and x2. Okay, well, this means that the vector, well, I make a little bit of a jump. x1 is negative 1/3 t, x2 is negative 1/2 t, x3 is t. Now, this vector will be in the null space for any value of t. Okay, well, let's just let t equal 1. Then we get x1 is negative 1/3, x2 is negative 1/2, x3 is 1. Right there is a perfectly good vector in our null space. Okay, now we might choose to have integer components of this vector. So, you know, multiply every one of these by, let t equal 6, multiply every one of these by 6. We get an equally good vector for the basis. Any multiple of this vector will form a basis for the null space. And there are no other vectors because there are no other possible solutions to the equation matrix times your x vector equals 0. Furthermore, this basis will apply to the original matrix A, okay? If this matrix times x equals 0, then since these rows have all been obtained by row operations which don't affect the linear independence of the rows, it's going to be true of the A matrix as well. Again, we've talked about that. I'm just reminding you. Okay, so here is our null space. It's the set of vectors that are spanned by this set, which means in this case simply the set of multiples of this vector. Your row space is the set of sums of multiples of this vector and this vector, your C1v1 plus C2v2, where there's your v1 and v2, C1 and C2 can be any number, so I call that a sum of multiples. Well, check for orthogonality, okay? We take the dot product of this vector with this one, regard this vector as a row, put this vector in a column, and multiply them, and we get 0. We get negative 1/3 times 3, negative 1/2 times 0, and 1 times 1. Negative 1/3 times 3 is negative 1, 0 gives us 0, 1 times 1 is 1, negative 1 and 1 gives us 0. And same thing here. You're going to get, again, 0 and negative 1 and 1, they add up to 0. Your dot product of this vector with either of these is 0, meaning that this vector is orthogonal to each of these. It'll therefore be orthogonal to any linear combination of these. Because, of course, if you multiply this by 5 times this vector plus negative 3 times this vector, 5 times this vector is still going to multiply this one, dot product with this one to give you 0. You can prove that very easily. So, the null space and the row space are orthogonal. Okay? I didn't write that out in detail, but that was implicit from the fact that those are the only two spaces we've determined at this point. Also, you know, on the sheet everybody's working from, that's the way it's stated, okay? Okay, well, then the null space consists of all multiples of this vector, okay? Now let's think about where this vector is, and I'm going to use straws because we spent a large part of today's class just looking at what these vectors and planes would look like in three-dimensional space. Okay, so we have let's think in terms of x, y, z, or x1, x2, x3, the typical orientation of our vectors in three-dimensional space. And of course, this matrix, we well know, multiplies vectors in R3 and results in vectors in R3, okay? Well, this negative 1/3, negative 1/2, 1 means in the x direction, we go 1/3 of a unit this way. I guess I'm not going to use the straws because I want to get the components. 1/3 of a unit this way, okay? In the y direction, we go half of a unit in the negative direction. That would be half of a unit this way. So we go back 1/3 of a unit over here, half a unit, and then we go up 1 unit. So we're going to go up 3 times as far as we went here and twice as far as we went here. And that's going to give us a vector that's, well, okay, we start by going down in the x direction. The vector is going to have a slope below horizontal, a slope of negative 1/3. So there's about a slope of negative 1/3, but that's in the x direction. Okay? In the y direction, we're going to go with a slope about negative 1/2. And in the z direction, slope of about 1. But again, the point is, we come over 1/3 of a unit, half a unit, and up 1. That's going to have us oriented in this direction, okay? So here we are vertical, and we tilt a little ways this way, tilt a little ways this way. There's our vector, and that's what I've depicted by this yellow line. I've depicted an arrow here that might represent our vector, our basis vector, but then I've extended that into a line. And I've labeled that the null space, labeled it in yellow. Okay, now, and actually I think what I did in class, I did multiply this vector by 6, so we get negative 2 here, negative 3 here, and 6 here. Still, same idea. So this null space, we can see kind of going back into that octant there. Okay, I'm not going to number them, but it'd be your 3rd octant. Your row space vectors are 3, 0, 1. So in the x direction we come out 3 units, the y direction we don't go anywhere, and in the z unit we go up, in z direction we go up 1. So we come out 3 units in the x direction and then up 1 unit, so there's our vector. Okay, now I'm going to turn it so you can see its slope, but there it is. Okay, that would be this vector from the origin out to this point. In purple, I've depicted the 0, 2, 1 vector. Okay, we go nowhere in the x1 direction, 2 units in the x2 or y direction, depending how you want it, what you want to call it, and 1 unit in the z direction. So basically we come over 2 and up 1. There's our purple vector. Okay, so we've got this vector on the x-axis and this vector not on the x-axis but in the xz plane, this vector in the yz plane, and we can see where our plane is. It's going to be in this direction. If I put something flat across here, it's going to form our plane. Okay? Okay. Well, we'll go on in a minute. We want to ask now, what happens if we apply A to a vector in the row space plus a vector in the column space?